So, welcome again to yet another video on axiomatic thermodynamics, and this is probably going to be the last on it before we move into semi-classical thermodynamics. And here we explain some very important thermodynamical potentials that come in handy in describing systems. We will also be meeting different physicists again, obviously Helmholtz, also Gibbs from our last video, and we are gonna also learn what enthalpy is and a bit also about what grand canonical potentials will be, which actually come from the grand canonical ensembles, which we will be discussing later in our semi-classical thermodynamics. Right, so let's get right into it. The Helmholtz free energy. What is it? We have a closed system, so there is basically no exchange of volume, so basically volume doesn't change, and the particles which are inside the system, so basically the microstates inside the system, they are not exchanged with the surroundings. The only thing that is exchanged is energy. So basically it's a closed system that exchanges energy with a reservoir in temperature T. So the volume is fixed and the number of particles are fixed. I denote the number of anything with a hashtag, so maybe I will be also using it in later videos. If you're not familiar with it, here's a chance. Good. So Helmholtz free energy. This is the potential, this is the energy that is defined. Since only energy exchange happens, that's why the term with entropy is subtracted from the internal energy. Why do we name F? Well, because historically enthalpy has been named H. So sorry for Helmholtz, he cannot be putting his favorite alphabet into one of the thermodynamical potentials. Mostly by physicists, Helmholtz free energy is termed as the useful work that is done, that is obtained from a closed system, which also probably makes sense because the only thing that we don't really take into account is the energy exchange with the surroundings. The change of volume is basically how work is defined. If you remember this formula that we said before, that delta W is basically equal to minus B dV plus mu of dN. So what we generally consider as change of work is basically change of volume and change of the number of particles. And yeah, if the internal energy changes in such a sense, disregarding obviously only the entropy part, then it can be termed as useful work that is done by a closed system. Then if we move to the next, which is Gibbs free energy, we already know Gibbs from the last video. This is also termed sometimes by chemists as Gibbs potential. In this system, in this perspective, the system does exchange energy, just like in the case of Helmholtz free energy, but not only energy, even the volume can change. So I can sometimes also say that volume is exchanged with the surroundings. It basically means volume is changing. So volume is not fixed in this case, and as you would guess, if from the internal energy we subtract this term and this term, the only thing that remains is how it's the term that is explicitly with the chemical potential. So this is why the Gibbs free energy or the Gibbs potential is very loved by chemists, because it takes into account the chemical potential of a system. And in case of chemical reactions, they are generally spontaneous when the change of the Helmholtz free energy is positive or the change of the Gibbs potential is negative. Maybe I should write also here or. Right, so you can obviously see it from two different perspectives. And one should also remember that the Helmholtz free energy, so like the system that realizes Helmholtz free energy is, let me write it in this way, F is very physically difficult to realize. So it is very physically difficult to realize. Because obviously, I mean, if you have a change of, if you are doing work, then you generally, like if a system does work, you generally consider or you expect the system to be expanding in some sorts. Since it doesn't do that, it is a bit difficult to realize then. Right. The more historic approach, enthalpy. It is basically defined for a system that is characterized by the entropy, the pressure, and the number of particles inside it. So this historically took the alphabet H, again sorry for Helmholtz. We have the inner energy plus the work that is done by expanding the volume. Here I have made a mistake by writing D here because we are not taking into account our infinitesimally small change of volume. And as you would also remember, this E is basically equaling Ts minus PV plus mu n. So there is no surprise that this comes out at the end. And in the end, we have our very own introduction into the semi-classical thermodynamics that is going to come in the next videos. This is basically an open system. It is the one that is mostly researched these days in thermodynamics. We have a lot of quantum mechanics that goes in open systems. But yeah, for an introduction, we have the open system, which basically means, again, if you remember from our first video, that then the number of particles can also be exchanged. So in such a system, the energy and the number of particles are not fixed. And we generally denote it with K from the German name of canonical. And it is equaling to the inner energy minus this term with entropy and this term for the chemical energy, the chemical potential, sorry. And that is basically the potential that comes because of the change of volume. We would be talking again in details on the grand canonical ensembles, and then we will come back to the grand canonical potential in later videos. But I hope this video helped you. If you liked it, please press on like and share it with your friends, and please press on the subscribe button if you find the channel to be useful, helpful for yourself, and if you wish for more videos. That would really motivate me. Thank you once again. Bye bye, and see you all later again in some other video.